Okay, all right, we're good. So you want to go to the slide?
Yeah, do you want to start because you're doing the honorable mentions, right? Okay. So this is good. Okay, can everybody hear okay?
And if I click on the link, it should go to YouTube, right?
Yes.
Okay. All right, let's get started. Thank you for people who are here in person, as well as for the people remote. It's the last class of the semester, yes. And then for people who don't know, there's chocolate in the front. So if you want to have a chocolate and celebrate the end of the semester, please go ahead. It's mint chocolate. So today we're going to go over some of those amazing projects we've seen. We have actually 4 winners and 6 honorable mentions. So let me go over that. Okay, so what is our, before we go into the project, a reminder that Professor Little has posted a peer project assessment form. Please fill them out before this Friday. It's just for us to assess individual contribution and how the team works together, and then to adjust our final grade. If you don't fill it out, we'll assume that everybody contribute equally. Okay, so what is the process of us selecting the final project? Where each teaching staff member nominate 4 of their project on their stack. And we met yesterday, we watched the video, we discussed the Python notebook and had a long discussion. And then the overall winners are selected by voting. Each one of us voted among the number of nominated project. We voted among the top 5 by scoring, and then sum over and sort them. And then the top 4 became the winner, and then last 6 become, the second 6 of them become honorable mention. So as a reward for best projects and honorable mention, each team member will get 6 additional points to their existing grade, which is roughly 120% of the possible grade for the final project. The honorable mention will get extra 3 points into their existing grade. And then they will all be listed under our website under the Hall of Fame. Okay, so I am going to start with the honorable mention. There are 6 of them in no particular order. This is called good bad company classification with machine learning. And the student are Joe, McVicker, and Malo. Actually, I'm going to give up on pronouncing the names because I'm going to butcher the names. Apologies. Here we go.
So after the Fed began to raise the interest rates last year, the market is more important. It's more important to have a balanced strategy in to construct a portfolio. Therefore, for our project objective, we are looking for construct a
Sorry, just a
portfolio
second.
of good
It's
company.
not very loud. I think this is the maximum audio for your computer for some reason.
Turn up the Zoom audio maybe?
Yes.
So escape here, go to the Zoom settings.
Sorry, guys.
Sorry. Audio settings at the bottom.
Yes.
Try that.
Are we still sharing?
Yes, I think so. No, we did. Okay, we stopped it.
And bad company in the short term for us to long or short stock. So for our project, we are using SingFine as our API, and we are pulling out the companies' trading prices, and also about their fundamental data, such as their.
Sorry, I'm going to start from beginning. I just
financial-
realized. Let's start from beginning. Apologies.
So after the Fed began to raise the interest rates last year, the market is more important. It's more important to have a balanced strategy in to construct a portfolio. Therefore, for our project objective, we are looking for construct a portfolio of good company and bad company in the short term for us to long or short stock. So for our project, we are using SingFine as our API, and we are pulling out the companies' trading prices and also about their fundamental data, such as their financial matrix ratio and growth. Yeah, I'll pass to Adam to discuss how we done this analysis.
Okay, yeah. So basically, the thing that we wanted to predict with our machine classification is the weekly return. And so if we buy today, in a week, are we going to make money or lose money? And so we train this on data from the past. And as you can see, it is centered around 0. And yeah, I'm just going to move into the classification. So we chose classification because we just needed this hard decision of whether we're going to make money or whether we're going to lose money. And there's a lot of different factors going into that. So this was the best method for us. And so the first model that we used is k-nearest neighbors. And for this model, you can see here we have the printout. We have a okay accuracy score around 57% on the test data. But you can see from our matrix that we actually are heavily biased towards predicting that companies will make money. And that's because we used a lot of really good companies, like leading companies and very successful companies. And so that did slightly bias our data. And so it just makes our data slightly less applicable for poorly performing companies or companies that are more volatile. And so in SVM, this, we don't have the printout because we ran it a few times, but the SVM model had really bad accuracy, around 53%. And that's just because it always predicted that we would make money. And just in our actual data, around 53% of the time, that was true. And so the SVM performed pretty badly because it just made that assumption. And then the random forest actually performed the best. We don't have the printout, but the information is here. We had a 76% accuracy on the test data, which is pretty incredible, and a 99% on the trained data. And so basically, even though we are pretty limited in that we are only working on successful stocks and we're only working in a very short term and we don't actually take in market information, as long as you keep those factors into account, we actually perform pretty well. And so, yeah, we would say that we definitely were successful and then we had a 76% accuracy with those specific conditions.
All right. So if you do make money with your program, our cost only takes 1%. All right, the next one is hate crime data analysis.
Hi, our group consists of Ariana, Marnie, and Aaron, and our project is Hate Crime Data Analysis. Recently, there have been numerous high-profile hate crime cases in media with new attention on Asian American targeted hate crimes. To investigate the effects of these hate crimes, we have analyzed data from multiple sources.
The summer months had higher rates of crime than winter months, which could possibly be due to fewer people being outside at lower temperatures. The year with the most hate crimes was 2020, followed by 2001. Additionally, California committed the most crimes, followed by New Jersey and Florida. 71% of all hate crimes were committed by white individuals. Most of the crimes were in residential buildings or on the streets, and most of the crimes were biased against Black individuals. The most common types of crime were simple assault and intimidation. Here are the overall time graphs for the number of articles about hate crime published and the monthly occurrences of hate crimes. The first graph is the raw data, and the second shows the data with a rolling average over 4 months.
Displayed here are two graphs showing hate crimes committed versus number of articles posted. Linear regression was performed on the full data and without 2020, and both have high R-squared values. The model shows a positive but small relationship. For an increase of 100 hate crimes, we would expect to see just under 1 extra article in the month. Here the graphs show the number of articles being posted by month after January 2009 all the way up until April 2022. The bottom graph also includes a 4-month rolling average being plotted over the number of articles posted by month.
Looking at the number of hate groups by state over the time period 2000 to 2021, hate groups were more concentrated in the South until 2010, when rates began to increase in the Northeast. California, Texas, and Florida consistently have the highest number of hate groups. We used data on whether states passed government resolutions against AAPI hate. We looked at two different outcome measures, whether a resolution was passed at the state level and whether any government body, state, county, or municipal, passed a resolution. We converted the total number of hate crimes with AAPI victims, and hate groups to per capita measures and used a scatterplot matrix to examine variable correlation. We plotted the data in 2 and 1 dimensions, since the first dimension explained 50% of the variance. For both, we noticed that New Jersey was an outlier. We created cluster heat maps with and without New Jersey to get a sense of groupings in the data. We then created classification models for the outcome of a state-level resolution. The SVM classifier and the KNN classifier both had a maximum accuracy of 0.6. We also ran the classification models with a second outcome variable of any resolution in the state at any level of government. The SVM classifier had an accuracy of 0.8, and the KNN classifier had a maximum accuracy of 0.82.
Thank you.
Let me try share again because I think yes. Okay, good. Where's your keynote?
I think it was just open in PDF.
Oh, it was PDF?
Yeah.
Oh, yes. Okay. Next one is on prediction of national park rating and fees from national park features. What is this one?
National parks are a highly valued amenity within the United States, with an estimated $15 to $20 billion spent by visitors per year towards them. More recently, visitation to U.S. national parks have been increasing. As a result, managers in these parks must respond quickly to increasing visitor-related challenges while keeping national park visitation a positive experience. That's where we come in. We have 2 central aims in this project. Firstly, to investigate what contributes to park visitation and try to predict future visitation numbers. And secondly, to create a rudimentary park recommendation system. These aims can help inform park policies, reduce barriers to traveling to national parks, and possibly even aid the formation of new national parks. We obtained data from a few sources, including the National Park Service API, US Census Bureau, and Google Trends. We started by collecting features from the National Park Service API. We combined visitation numbers from the National Park Service dataset with the API data we just collected. We also combined data from city and town GPS coordinates with the population values for the city. We used these coordinates to calculate the distance from national sites to all cities and towns. For the regression model, we collected the sum of all city populations within 75 miles of the national site as a predictor. For the recommendation system, we also use these coordinates and distance techniques to get some fun, personalized data for the user, which we'll talk about in a minute. The end result was a dataset with 464 national sites and 302 features for those sites. So what do we do with all this data? We started by creating a correlation matrix, which is seen here. Next, we made several linear models. Our best model predicted the log of visits with an adjusted R-squared of only 0.415. Unfortunately, the biggest predictor was entrance fees, which is likely not causative towards visitation numbers, but rather visitation numbers likely affect entrance fees. So this is probably more of a correlation. Overall, this shows a low predictive power of our model.
Hi, I'm Apurv, and I'm going to talk about forecasting the number of visits using Google Trends and historical visitations data. For this model, we used open source data. The results obtained were very promising. Using the linear regression model, we were able to predict the number of visitations to a park with 99.8% accuracy. We also tried random forest classification model, which even though was not as accurate as linear regression, it gave us 90% accuracy. This is very promising data in terms of real-world application. It can help national parks prepare for an influx of people and help in managing their resources efficiently to accommodate people without causing damage to resources. We visualize the data as seen in Python files. Next, I'm going to talk about the most fun part of this project that we created. We used a huge data set that we created for regression to also develop a portal that can be used to recommend parks to users. I will walk you through how this will work. For this part, run the recommendation system code and use the keyboard to enter your preferences. You will be given a series of activities, amenities, and geographies that you can answer by entering 0, 1, or 2. 1 means you want that activity in your park. 2 means you prefer if that activity was not present at the park. For example, I don't like going to the oceans very much, so I would prefer if the park was not at the oceans. Finally, entering 0 would mean you don't care about that activity. When asked, enter the maximum entry ticket fee you are willing to pay, and finally enter your 5-digit zip code. When this is done, press enter, and a recommendation system will give you a list of parks in the order that is closest to your location. Once you have a list, you can type in the name of the park that you may want to know more about, and it will give you a list of activities and topics, and also a list of surrounding cities if you want to plan a trip to the neighboring places. Finally, we conclude from our analysis that predicting visitation rates is not straightforward, and there are more things that make a park popular than what we can quantify. We have shown that a forecasting model using Google Trends is very accurate and can be immensely useful to national park authorities. And finally, the recommendation system with more refinement and UI can be of great practical use to travelers.
All right, that's national parks. All right, the next project is called The Worst Crime is 2020, maybe 2021, and also. All right, let's see.
Hello, our team has me, Jessica Jung, and Trish McCauley. We'll be presenting on The Worst Crime is 2020. Year 2020 was an interesting year full of unexpected events, and we decided to focus mostly on the effects of 2 events: the announcement of the stay safe, stay at home orders in Utah, and the release of the body cam footage from George Floyd's death on crime rates in Utah. We used the data from the NIBRS FBI crime data and cleaned up the data to make it suitable for our project. The one thing I want to mention is the correlation matrix heat map from the crime data. And as you can see, there aren't a clear correlation between demographics and the offense type. And this is the animation of the time series of the daily arrest in Utah. And as you can see, the lines are a little noisy. So after doing the moving average, we were able to smooth the line, and this is what the trend looks like. And this is the graph of the different crime time break over the year of 2020. And this is the, after doing moving average to make the line smooth, this is what it looked like in individual crime type. And Tricia will talk about the regression.
What we did for the regression was that we broke our data down into separate intervals based on the trigger events that we selected, and we tried to implement multilinear regression. However, as you can see, what we found was that based on the R squared, which is almost 0, there's basically no consistent slope, and that linear regression was probably not the best test to use on our data set. And so as you can see here, the original data is overlaid in the background. And as Jessica mentioned, it was very noisy. And so what our smoothing attempted to do in each interval is to identify the major trends. However, it was still not successful because, as you can see in the first interval and last interval, the data does not have a consistent slope, which means that it cannot be predictable using a linear model. And in the second interval, there just wasn't enough data at the end to actually identify many major trends that could be applied to the population. What we ended up doing was an exploratory analysis on the breakdown of characteristics and demographics for arrestees. And we decided to actually implement the Dickey-Fuller test of stationarity because we found the longitudinal analysis was very successful, and we just wanted to uphold the results that indeed these were unexpected events, they're not forecastable or seasonal. And based on the p-value, we can see that it's above 0.05. So it means that the data does have a unit root and is not stationary as expected.
All right. So next one, comparing classification method for predicting structure defensibility in the wildland-urban interface.
Our project compares different classification methods using machine learning techniques such as decision tree, random forest, support vector machine to predict structure defensibility in the wildland-urban interface, also known as the WUI. These classification methods are compared in variable importance plots to determine not only which model performs best, but which variables are most important in making the defensibility determination.
We acquired 2 data sets from the National Park Service and the National Interagency Fire Center, which were collected by professional wildland firefighters. While the data were collected according to the same guidelines, only 10 useful variables matched across the data sets: triage category, defensible space, safety zone, fuel type, water supply, siding material, roof material, latitude, longitude, and building use. Each of these variables had to be cleaned in some way, including renaming, removal of NANs, recategorization, or casting as different type of variable. A total of 32,000 records were left after cleaning was completed. And we did some data exploration, including bar plots for visualizing our categorical variables and geospatial plots for latitude and longitude, using color coding to see the distributions across source and our target variable triage category.
After the cleaning, we converted our categorical variables into dummy variables and then split our data into testing and training from 75 training and 25 testing. Next, we looked at decision trees. Despite giving high accuracies with training and testing data, the decision tree was likely severely overfitting our data. Even with tuning, our training accuracy remained nearly 100%, while testing accuracy lagged much further behind.
Next, we tried a random forest, which initially had a lower accuracy than the decision tree model, but with hyperparameter tuning, we were able to get a training accuracy of 83% and a testing accuracy of 82%, likely reducing, if not eliminating, the severe overfitting resulting from the decision tree.
Lastly, we decided to use an SVM. The SVM gave us the lowest accuracy even with hyperparameter tuning. It also did not deal with the nonlinear nature of our data very well and led to significant processing times when attempting to tune the model.
We found that the random forest classification method is best suited for this data. Our best model showed that the most influential variable were the presence of a safety zone, fuel type, defensible space, and latitude and longitude. This project could be expanded to include more continuous variables and other geospatial data to further understand what is impacting structure defensibility to reduce risk to structures in the WUI.
Cool. I always have to see this. Okay. The next one is exploring data analysis of PC games.
My name is Nate Masson and my partner is Andrew Youngberg. For our project, we wanted to explore PC game data from Steam and Twitch to see if we could use that data to build a review sentiment analysis model and a model that could project average concurrent player counts. To start, we used Python's request module to get batches of JSON formatted reviews from Steam's API. And with this, we created data frames, cleaned them up, and saved them for exploration and analysis. Looking at review data for a game called Terraria, which returned the highest amount of reviews, we see that most of the reviews are from the last few years. Most of the reviews are less than 200 characters in length, and most of the reviews were written by players who recommended the game. After filtering through the review text to find some of the most common words, we generated word clouds for positive reviews and for negative reviews, and words common between the two were removed before sentiment analysis. Next, we ran some pre-processing on the review text and built multiple text classifiers. 2 logistic regression classifiers and 2 multinomial naive Bayes classifiers were trained, tested, and optimized. And the naive Bayes model with TF-IDF vectorization slightly edged out the others with a weighted F1 score of 85%. A new set of reviews was requested, cleaned, and pre-processed, and the trained naive Bayes classifier was used to analyze the reviews with 91% accuracy. And these results were then used in the next part of our project.
After analyzing the review data, we moved on to analyze the concurrent player data. To do this, we scraped and collected data from steamdb.info on the average number of players, average number of viewers, price history, and patch history for a selected number of games. With these variables, we trained 2 models using data for the game Terraria, one linear regression model and one nonlinear regression model. The nonlinear model outperformed the linear model with an R-squared value of 0.822 versus 0.792. One question we had was whether this model could be generalized to other games. We tested our model with data for Warframe and Path of Exile. In the Warframe test, it is clear to see that the general shape of the predicted values seems to follow the actual values. We can even see points in time where they almost line up perfectly, like between July 2020 and April 2021. We used the Pearson correlation coefficient to judge the accuracy of the model, and we found it had a correlation coefficient of 0.42 and a p-value of 3.07 times 10 to the minus 11. Similarly, the path of exile predictions followed the unique shape of the player count. However, the model almost always predicted a higher number of players than there actually were. For this test, the linear model outperformed the nonlinear model with a correlation coefficient of 0.63 versus 0.59.
All right. So before I go to the winners, for people who are remote, if you are, part of the honorable mention, please raise your hand. For people who are here, if you did win the honorable mention, please stand up. At least let's give everybody a round of applause. All right, so, and I'll pass on to Professor Little to talk about the winners. And then the winners each will get a backtrack calculator.
If they're here.
If they're here.
All right, so it's my pleasure to introduce the winners, again, in no particular order. First off, optical spectroscopic object classification by Alexander Millar and Rowana Rog. I'm probably going to mess up some of the names too, but here we go.
The final project description by Roregu and Alexander Miller is a Python model to classify astronomical data. Our data acquisition process involved a couple of steps, including FITS files, which didn't quite work. We did web scraping, which also returned invalid data. And then we did web querying, which did return data, but it did not return any quasars. We're using the SDSS DR17 website. So after that, we did write something in Python to inject the quasars, but then finally we were able to use the search tools SQL query to run a final query to get back 100,000 objects for our final data model. Once we had our model, we are going to run, well, we're going to clean it and massage it, but we're going to run dimensionality reduction on it. And our first one was a PCA. And in that PCA, we ran both PCA on data with and without auxiliary columns. So this section here is with the auxiliary columns, we get the number of components, but then our final graph here, we can see that there is no structure to the forming of clusters, and we can see some high variability between certain variables. Finally, without the auxiliary columns, we can see a much cleaner clustering effect here. We can start to see that there is some coherence and nothing dominating the variance there.
All right, so when we did our three-dimensional PCA, after removing the auxiliary columns, this is a three-dimensional view of it, and we have a lot more coherent bodies. So then we went into t-SNE, and we calculated a 2D t-SNE with and without the auxiliary columns. This is with the auxiliary columns. And we found that when we remove them, our correlation matrix becomes a lot cleaner. This is comparison of the two-dimensional t-SNE with auxiliary columns and without. Clearly, it's a little bit more coherent. So we started to go into the density plots of the different variables colored by class and tried to pick out what variables distinguished classes versus which ones didn't. For example, that was not similar to this one, also not statistically significant in distinguishing classes among quasar, galaxy, and star. Here we calculate three-dimensional t-SNE with auxiliary columns and without. This is a two-dimensional projection of it. Then we'd look at a three-dimensional projection. This is with the auxiliary columns, this is without. And we have our interpretations here. So this is multiple angles and views of the three-dimensional t-SNE without the auxiliary columns, which is what we ended up going with. And through rotations, you can see that you can follow coherent bodies through each rotation. And so that's what we ended up going with. And it kind of lines up with some things that we'd seen in relationships of our variables to the classes. So we also tried doing a t-SNE from our PCA output, and it did look pretty coherent at least from some angles, less from others. Took our dimensionality reduction and did some clustering on it. And then here's our final results and summary. In the end, it basically ended up being the SVM was about 96.4 accuracy and 96.8. It was kind of close there, and it varied with and without the auxiliary data. But compared to our k-means from the dimension reduced, which was 44 and 42%, that's a large improvement. And actually the 44% was with our auxiliary data, not our reduced data. And then for random forest, 98%.
All right, so let's go to the next one. Okay, so next up we have predicting the 2023 Basketball Hall of Fame class using machine learning by Kobe Toem.
The Basketball Hall of Fame honors those who have shown exceptional skill as a player, coach, or other major contributor to the sport. Though anyone can be considered as a Hall of Famer for many different reasons. However, using Python, I will train 2 classification models to predict current and recently retired players' chances of becoming a Hall of Famer and potential first ballot based on previous Hall of Famers. A first ballot Hall of Famer is a player who was inducted on their first appearance on the ballot and known as one of the greatest of all time. These players include Kobe Bryant, Michael Jordan, and Kareem Abdul-Jabbar. As of 2022, players are eligible for the Hall of Fame after they have been fully retired for at least 3 years. Knowing this, here are some questions to consider. Before answering these questions, I'll have to scrape player stats with Python and Beautiful Soup. Basketball Reference is a great website to scrape and gather team and player information, and conveniently, there is a directory page containing all NBA players. First, let's take a look at Kobe Bryant. By right-clicking on an element on the page, we can inspect it as an HTML and CSS code. Next, I will import the Beautiful Soup library into Jupyter Notebooks and use my custom functions with keywords, loops, and conditions to extract the necessary stats. From there, we have extracted all of Kobe Bryant's stats and awards. All NBA player stats are extracted and stored into a data frame, then cleaned and converted into CSV files.
O'Neal got a piece of it.
Before visualizing the data, I'll need to filter the CSV files to players who are eligible for the Hall of Fame. I'll grab every player who was retired and last active before 2019, since the 2022 Hall of Fame class has already been inducted. Now when visualizing the data, I used bar plots to look at Hall of Fame players per position and team, as well as looking at the averages between Hall of Famers and non-Hall of Famers. Scatter plots are included to look at career totals such as number of championships and MVP awards. Finally, I've added distribution histograms to look at the frequency of seasons played, total win shares, and total All-Star and All-NBA selections. With this data, let's answer this question. First, we'll look at Patrick McCaw. He's a 3-time NBA champion. Although, would you consider him to be Hall of Fame worthy? By looking at his career stats, we can see he is mostly below average, and the biggest reasons he won those championships were because he played with 4 potential Hall of Famers. And even comparing his stats to Karl Malone, who has never won a championship, Patrick McCaw doesn't even compare. Looking at the scatter plot, Malone with 0 championships was a first ballot Hall of Famer, whereas a player with 8 championships still has not been inducted, so other factors have to be included.
Conference finals between the Celtics.
To find the most correlated variables among Hall of Famers and first ballot Hall of Famers, I used the correlation matrix. Any variables higher than a 0.5 were included as predictive variables for the classification models. Out of these models, logistic regression and random forest classifier were the most accurate, so let's go ahead and use these in our predictions. First, we'll check out the predictions for Patrick McCaw and Malone. In all seriousness, here are the results for all active players, with predicted first ballots bolded. Unsurprisingly, these 9 players are predicted to be first ballots and are top 20 in terms of Hall of Fame probability. I've noticed the random forest model has 7 All-Stars, 5 All-NBAs, 100 win shares, and 13 seasons as the minimum qualifications. The biggest first ballot snub on this list is Giannis Antetokounmpo. He's regarded as the best player in the world, and many would consider him as a future Hall of Famer. However, he only has 6 All-Stars, 5 All-NBAs, 87.5 total win shares, and 8 seasons played, so the model doesn't predict him as a first ballot Hall of Famer if he were to retire today. Plus, there are many superstars that have similar stats as him.
Nowitzki drives, goes underneath, lefty layup, banks it in.
Finally, here are what the models predict to be the top candidates for the 2023 Hall of Fame class, with predicted first ballots bolded. These are the top 10 candidates, though it is likely going to be these 4 who are going to be inducted as finalists. Although Pau Gasol and Tony Parker are just under the minimum to be predicted first ballots, many would consider them to be inducted as Hall of Famers in 2023. And obviously, Dirk Nowitzki and Dwayne Wade are predicted as Hall of Fame locks.
Middleton, Giannis trailing the lob. Oh! Giannis Antetokounmpo from Chris Middleton.
Okay, very nice video. So, okay. All right, next up we have Analyzing Induced Microseismicity at Utah Forge by Faris Khan, Patrick Bradshaw, and Barrett Kilroy.
Hello, my name is Barrett Kilroy, and my other 2 group members are Patrick Bradshaw and Faris Khan, and our project is Analyzing Induced Microseismicity at Utah Forge. So the main questions that we wanted to answer with this project are, can injection parameters be used to predict data about the seismic events at these sites, as well as which features from the injection data are most important in predicting seismic activity data? As well, are the models for both the Utah and Switzerland sites similar? And finally, how does our model compare to the predicted maxima by the McGaugh relationship?
Our data comes from 2 locations, Basel, Switzerland, and the Utah Forge project. Both sites have an earthquake catalog and an injection time series. We combine these by iterating through our catalogs at every injection time step and counting nearby events and recording the largest magnitude. The injection data comes from a variety of sensors from around the injection operation, as illustrated here. You can visualize the injections as a function of time or as a function of injected volume.
For the analysis, we performed regression using injection parameters to predict maximum magnitude and frequency of earthquakes in a 12-hour window. That's 2 regression tasks for 2 geological sites, and what we're after is a feature importance telling us the most important injection parameters. We used a variety of regression methods for our 4 regression tasks, and across the board we saw fairly good performance, as shown by these parity plots. One way we interpreted feature importance was just to look at the coefficients of our linear model. Another way is to look at the mean decrease in impurity for tree-based models, but this really only shows how your model is making decisions on training data. Our final approach was to use permutation-based importance, which basically randomly shuffles certain features to see how much your model performance decreases after doing so. Some limitations of our analysis was that we didn't perform a time series analysis, and our feature importance is a little misleading.
If we compare impurity-based importance to permutation-based importance, we can glean implications about our data. Impurity-based importance is biased towards features with high cardinality or number of possible values. Permutation-based importance is biased against features with high levels of correlation with other features. For Basel's frequency, features like flow in and cumulative volume have high cardinality but also correlate with the pressure features. This is also the case for Forge's maximum magnitudes. The permutation-based importance is noteworthy especially because it contradicts deterministic models which relate volume injected to maximum magnitude.
Okay, and we've got one more, which is Deja Brew by J. Ray Corcuera and Brianna Mendoza. So this is our last winner.
Coffee is a drink that has been found from all corners of the world and has been around for hundreds of years. However, the question we pose is, where does the best coffee come from and why? To To explore this question, we obtained our data from this website called Coffee Review. Coffee Review is a group of coffee enthusiasts who've tried thousands of coffees and documented their experiences here. The website contains over 5,000 reviews, which we retrieved and stored into a data frame using web scraping. Taking a look at the data frame now, this is what the data looked like after web scraping it. After cleaning the data and wrangling with it, this is the result. An important change we made was to simplify the name of the coffee's country of origin and append the latitude and longitude coordinates of the countries to use for our geospatial plots. We represented the roast level as a numerical variable where 0 is the lightest roast and 4 is a very dark roast. We split the Actron values, which are the color of the bean, and finally we converted the estimated price and calculated $1 per ounce by dividing the values. We first conducted some simple regression tests with the roast level and dollars per ounce variables. The roast level follows a downwards trend, which indicates that darker roasts tend to receive lower ratings on average. As for dollars per ounce, the trend is nonlinear and follows a logarithmic path, which could mean that at a certain point, increasing the price won't significantly increase the rating. Moving forward to our global analysis, here we see a heat map of all coffee origin countries and their average rating. The first cluster we see is Central and Southern America, with countries like Panama and Colombia being the best out of them. The second cluster is Africa, whose best countries are Ethiopia and Kenya. We found the Asia cluster to be insignificant because all of these countries had less than 10 reviews to their name. Therefore, we omitted them.
Consider the distributions of both Africa and the Americas. We can see that while the Americas have some very high-rated coffees, there are also significantly more low-rating coffees, opposed to Africa, who only has a few low-rated coffees, but for the most part is very consistent. Let's look at the African countries Ethiopia and Panama's distributions. Ethiopia's distribution follows a fairly symmetrical model with a median rating centered around 93, in comparison to Kenya's distribution, whose mean rating is also centered around 93, but whose data is skewed slightly and has some outliers on the lower end. Since Ethiopia has significantly more reviews, it is understandable that the distribution has normalized. As for Kenya, there may just need to be more reviews before a more consistent rating occurs. Now let's look at South American countries Colombia and Panama. While the Book of Colombia's data falls at the higher end of ratings, a number of outlying ratings occur at the lower end. This may be due to the best of all worlds approach that Colombia tends to take when producing their coffees, using multiple methods and attempting to satisfy the likings of everyone they can. Whereas Panama's data falls succinctly on the upper end of the ratings, and whose data is almost perfectly normal with the exception of a few outliers. Even those outliers are still high. This could be due to the wet processes that Panama uses, incorporating a mix of their familiar Arabica trees. They are also known for their geisha blend, which was rated the highest at 98.
For our last goal, we created a coffee predictor program in Jupyter Notebook that is able to predict the coffee's roaster, country of origin, and rating given its roast level and price per ounce. If we use Coffee Review's latest review as a test subject, since this review is not included in our data frame, we can see that the program is able to correctly identify the country and roaster, but a little lower rating. We hope you enjoyed our presentation, and thank you very much.
All right. So those were really nice. Thanks everybody to our yeah, so let's see. Winning teams here.
Grab your chocolate. There's 4 different flavors. Congratulations. And for the winning team who don't have representations, you can pick it up later from my office. Oh, one bag per team. All right.
All right. Okay. So let me share this again. Actually, before I do that, maybe we can also just see. So people on Zoom on the winning teams, if you want to like raise your hand, we can, I don't know, have a virtual acknowledgement. And Kobe, yay!
All right.
Okay, great.
And for people who are here, we can also eat from that bag.
That's right. Okay, so great. So that was sort of probably the most exciting thing that we're going to do today, but we're just going to tie things together with a little recap of what all we've learned and covered in this course, talk a little bit about a couple of things that we didn't cover, and some additional resources for you as you go forward. Okay, so what did we learn? Lots of Python. So if you already knew Python coming into this course, I'm sure that was helpful. But if not, you've got quite the crash course for Loops, Jupyter Notebooks, all kinds of libraries, various Python data structures, including lists, dictionaries, series. And we looked at, cleaning data and aggregating data, and also got a little bit of introduction to version control with GitHub, et cetera. Okay, and then we also, we worked a little bit on getting data. You probably especially worked on that in doing your projects, but we discussed web scraping a bit, HTML inspectors, how to retrieve website information and parsing HTML code, et cetera. And then also various APIs, useful APIs, and databases. Okay, we discussed data visualization. Of course, this is critical for data science. Looked at some of the packages and libraries in Python which are helpful for that, Matplotlib, Seaborn, et cetera. And we talked about some different ways of plotting and visualizing the data, starting off with some real basic things like histograms and scatter plots for visualizing distributions and correlations. And then also moving into some more fancy things and visualizations for decision trees and graph layouts. Okay, and we did a little bit of statistics, hypothesis testing, and statistical inference, discussing different distributions, normal distributions, binomial distributions, how to do hypothesis testing, A/B testing, lots more that could be said, so much more that could be said really on all of these things, but we've covered a lot of ground. We spent some time looking at time series, specifically for financial data, getting and visualizing stock prices, looked at moving averages for smoothing out these time series and various trading strategies that you could develop just from the time series itself. Okay, and then we looked at regression. We saw a lot of regression going on in many of those videos, starting off with simple linear regression and then multilinear regression, and then a little bit of nonlinear regression where we take into account some nonlinear variables and interaction effects, and how confounders can really make interpretation challenging on some of these models. Okay, and then we looked at classification. So we had a handful of methods to help us with classification problems. We looked at k-nearest neighbors, decision trees, support vector machines, neural networks. We talked about generalizability and cross-validation. Those were really important concepts for a lot of the methods that we went over. And also looked at TensorFlow and scikit-learn. I guess we'll talk a little bit more about that when we go over the neural network stuff. And then we sort of shifted into talking about unsupervised learning in the context of clustering. And we went over various algorithms for doing clustering, including k-means, hierarchical clustering, dbScan, how we can sort of visualize hierarchical clustering results in dendrogram plots, and also how to do all these things in Python. Okay, and then continuing on in the unsupervised learning flavor, we discussed dimensionality reduction with a focus on principal component analysis, how we can actually take a really high dimensional data set and visualize it in a small number of dimensions. This is sort of the general philosophy of dimension reduction in general. We focused on linear dimension reduction, although we saw a couple other methods at the end. Okay, natural language processing. So we had a lovely guest lecture on that, and went over some tools for natural language processing, semantic analysis and regular expressions. Okay, and also networks, including centrality measures, PageRank, pathfinding, and graph visualization. That's also quite a big topic. Lots to be said on that. Okay, and then one of the last things that we discussed was neural networks and deep learning. This was sort of a very flexible tool that we could use both for classification or regression. Those were the contexts that we focused on. Can even be used more broadly for unsupervised learning and other kinds of things. We saw that this was a really powerful tool, but also difficult to train, requiring a lot of data and a lot of computational resources. And sometimes the results can be difficult to interpret. It's a little mysterious exactly what's going on. Okay, we also talked about ethics in data analysis, using some materials from Dr. Yagadish's course from University of Michigan. We talked about what are ethics, what is informed consent, who owns the data, are algorithms fair, what are the consequences to society, to what we do as data scientists. Okay, so we covered a lot. So you should be proud of yourselves for learning so much over the course of one semester. A couple of things that we didn't talk about, so a couple topics that we're missing from this course that maybe you'll pursue in the future if you're interested in, is reinforcement learning. So we really focused on unsupervised learning and supervised learning. In the unsupervised context, right, we have some input X, and we want, and basically to summarize it, you know, or maybe we want to come up with clusters based off of the data or some sort of summary of the data. In the supervised context, we have something that we're trying to predict, like a label or a function. In reinforcement learning, what we're trying to do is we're trying to learn what action should I take in order to maximize a reward. And this has some connections with optimal control. And this is a statistical model which can evolve over time. So these actions that you're taking can change in time. So that's another big area that we didn't touch on in this class. Another thing that we didn't touch on is recommender systems. So in recommender systems, you might think of Netflix, where you have a bunch of users and you have a bunch of movies, and maybe, maybe each user has rated a few movies, maybe some have rated like 10, maybe others have rated like 100. But they've only rated a very small number of the movies that are actually available on Netflix. But what Netflix would like to do is it would like to take that information of what movies they have rated and then make recommendations. So based on what you have liked and what you have not liked, we can infer based on what other people with similar preferences have liked and not liked, make some recommendations of movies that you would enjoy. So basically what's going on here is you have like some big matrix with a bunch of missing entries, which you want to fill in. And this is a math problem called matrix completion. And the reason that you can have some hope of being able to do this is essentially because there's a low dimensional structure in that matrix. People's movie preferences aren't actually really that complicated. So that's why we have a hope of doing this. This is kind of a fun, it's a fun problem. And Netflix offered $1 million to the winner of a competition who could actually do the best job at generating these recommendations. Okay, another area that we haven't really discussed is the area of Bayesian methods. There's a whole lot of things out there in the Bayesian framework. And what is it in a nutshell? Of course, there's lots of different varieties, but the basic philosophy is that you start off with some data, which call it X. And then you have parameters in some probabilistic model, call that theta. And the prior distribution will be some distribution over parameter space that you put on your model parameters. You may decide what's best, or you may have some like domain expertise that makes you think a certain prior distribution is reasonable. And then what you can compute is something called a likelihood function, which is basically the distribution, the conditional distribution of the observed data given the model parameters theta. So what's the probability that I observe the data that I observe given, or think of it as if these were the true model parameters. Okay, and so once you have that likelihood function, you can construct a marginal likelihood function by integrating that thing multiplied by the prior distribution. And then at the end of the day, you can turn that into a posterior distribution. So the basic idea here is that what can you compute from your data? Well, you can compute the probability that you see that data given some model parameters. What would you like to know? You would really like to know what's the probability of those parameters given that I have observed this data, because this is actually what, you have observed this data. And now you want to sort of say how likely certain parameter values are. So the Bayesian method is basically a trick, kind of flipping this problem around and relating the probability of theta given x to the probability of x given theta. Okay, and so that you can do that with Bayes' theorem, and then this becomes proportional to the probability of x given theta, which is computable, times the prior distribution. Okay, and so those can be, there's definitely different schools of thought. Some people love Bayesian methods and some people hate Bayesian methods. So depending on, where you fall in that framework, a lot of people either love this or hate this. Okay, another thing we didn't have time to talk about is research reproducibility. But basically, there's a bit of a reproducibility crisis going on in research today, particularly in psychology and medicine. And some of the reasons for this are publication bias, cherry picking, small sample size, irreproducible experiments. One thing that we can do to help this situation is try to make all of our research projects and publications reproducible by actually making the code available that we use to generate these results. So whenever possible, if we can, make the code available, other people can reproduce it, other people can compare with their methods a lot more easily. Okay, I think I'm going to hand it over to Professor Phillips for the last bit.
All right, so I just want to make a comment. My favorite reinforcement learning is actually watching my, now he's 7 years old, but when my son was 6 years old, he runs around the house, he runs straight to a wall, falls down, cry. And then a few days later, runs straight to a wall, falls down and cry. And I was just sitting there watching him and figuring out when he's going to learn. That's exactly reinforcement learning. At some point he will learn, it's painful, he will not do it again. And if next time you think about reinforcement learning, that's sort of like a human model of it. Anyway, so where do we go from here, right? So consider this to be your introduction to sort of data science. There's other available resources at University of Utah. So the first one is Utah Center for Data Science. I'm actually the outreach, the director of outreach for UCDS. So we actually have, during the semester, a weekly public seminar. So if you go to the webpage, you can sign up. Some of those has been online, some of them will be in person. I assume if the pandemic is hopefully over in the fall, then most talks will be in person. And then some of those seminars are also recorded, and it's a very nice mix of application of data science in various domains. And we also sometimes get industry partners to also give talks about how data science is in the wild. So it's a very interesting resource, and I highly encourage you to go. And again, when pandemic is over, we will have the Data Science Day, where we are going to have a one-day event with a keynote speaker, panelists from industry, and job fair. But that hasn't happened for a couple of years. There's a bunch of courses in math, stats, and computer science of interest. If you found a subset of things you learned in this class interesting, here are some of those amazing courses you can help build certain components in your skill set. And you know, of course, I'm very biased. I teach one of those visualization courses. Okay. There's also a degree of Master Stats, MStats degree. And you can go to their webpage. It talks about what is a course requirement and so on. There's also in School of Computing, we have a master degree in computing under data management analysis. And of course, I'm one of those core faculty there as well, and designed for sort of full-time students to pursue, after undergrad, to pursue a master degree. If a subset of things are very exciting, but you really don't want to do a new degree, you can also obtain a certificate in data science. Here are the two links. There's a certificate for data science for undergrads, and it's you can more or less treat it as a minor. And for graduate student, it's designed actually for professionals working full-time and not a CS graduate students, that you can also get the certificates in data science. For example, this specific class is actually one of those class that is part of the certificates program. Okay, so to wrap up today, hopefully I'm not over time. Okay, so what we would like is for course evaluation. So if you can take the next 5 minutes to put in the course evaluation, we will really appreciate. It's scf.utah.edu. You log in with your UID. The evaluation is very important for the teaching for faculty here, and then also the TA, to understand what is important for us to improve. And as a small bonus, that if more than 70% of evaluation is completed for this course, everybody will get 0.5% bonus toward their final grades as a small token of appreciation. So scf.utah.edu. Specifically, we want to get the following type of feedback: were your expectations met? What else would you have liked to learn about? What was the, is ordering of the material reasonable? Did you feel that you were prepared when you took this class? And are the prerequisites appropriate? Was it too much work? Was it too easy? Was there too much math or too little math? Is there too little programming or too much programming? And did you like Python, Jupyter, GitHub combo? Did you enjoy the project? I hope you did. And should we have had exams? This is traditionally a non-exam course with final project. I see somebody shaking the head. Okay, so if you could spend some time, complete this. I'll end today's lecture with this slide, so if you could finish that. And finally, I'd like to thank everybody who participated and have come into lectures, especially those ones have made the extra effort to actually come in person. And of course, for students who have asked questions, actively participated, come to our office hours. We love interactions with you, especially during pandemic. I don't want to talk to an empty classroom, so thank you very much for coming. And also, I'd like to thank our guest lecturer, Yitudro Chad Tobas. By the way, Chad's recorded video is accessible through Canvas. It offers a very, very different perspective from nonprofit organization on data science. And finally, and not the least, to our amazing TAs, Minzhe, Haoyu, and Prashant. Thank you very much. So I'm going to leave this website here, but that would conclude our class. A few last minute announcements. So homework 8 is going to be graded. Hopefully you will release a grade in a week. Again, you will get time to, roughly a week time to kind of have any regrading requests for homework 8. For the final project, we wouldn't have the luxury to give you 1 week of time, but we'll try to give you a day when we release the grade. For the final project, you will have a day to do any sort of regrading requests, if any. We also will give you a few days time to go over sort of if there's any clerical error in the grades. It's not for regrading requests, but just making sure that your accumulated points are accurate and so on. And for that, I'm going to end the last lecture of the semester, and everybody have a nice and safe summer semester or summer vacation. Thank you very much. Oh, yes.
Also, you can turn in activities.
Oh, yes. Finally, if you, yes,
Turn in your activities.
put in your activities, because that's part of your final grade. You can put any 5 out of this many class activities submitted through Canvas, because that's 5% of your final grade. Please try to complete them before April 29. Okay. All right. Thank you, everybody. All right. We're done.